So do you have any questions? Any questions? Okay, fine. So let us start the mean value theorems. So in the mean value theorems, so we have mainly three mean value theorems, and the fundamental theorem is Rolle's theorem. And the second one is Lagrange's mean value theorem. And the third one is Cauchy's mean value theorem. Right? Now, these mean value theorems you can understand by common sense. So these are very, very fundamental theorems which you can make out very easily. And then here, suppose let us take one case wherein a person is running or he participated in a running race. Now let us say we have drawn the graph of the time versus his speed. So he is trying to change his speed continuously with respect to time. That means he is having certain acceleration. Now here we have identified one point. Let us say when he started traveling, so he started with certain velocity, and then let us say he keeps on increases and increases, and at one fine stage he takes back and finally he stops at this particular point. Now we have identified one place on the path. Let us say the location is at A. So when t is equal to A, we tried measuring his velocity, and that's what actually we call this as f of A. So this is the velocity of the person at point A. And then we tried making one more measurement at one more point. So that is at B, and then we found that he is having the same velocity. So f of A is equal to f of B. So we have identified the 2 points wherein the velocity of the person is same at both the places. One is at location t equal to A, and another is at the location when t is equal to B. He is having the same velocity. Now immediately we can conclude one fact, that so first time when I saw him, he tried increasing his speed, but next time when I saw him, so he is having the same velocity as I have measured at the earlier case. That means I can conclude that he has taken a somewhere there is a turn in the velocity. That means he started degrading his velocity at least at one location, correct or not? So that location is this point where he keeps on increases his velocity, and then at one point he started reducing his velocity, correct or not? That is the conclusion, right? So this conclusion is exactly what Rolle's theorem states. So if the function is continuous, here actually one fact is that, so this guy is having the velocity is taking turn. That means he started degrading his velocity, which essentially means that the derivative of this particular function at this location is definitely equal to 0. So this is point C. At point C, the derivative should be equal to 0, because for any curve, the gradient value is nothing but the slope of the curve at that particular point. So the gradient will be 0 at this location. This is the point of maximum or minimum point, correct? Now here the conditions are the base. So in my analysis, whatever I have done just now, so there are certain conditions associated with it. So the assumptions there is, so the same person, he tried continuous travel till this particular point without any breakage. Suppose if he drops out of the running race at this location itself, then this statement of no use, correct or not? Got it? So that means you cannot straight away conclude that, so if this person, right, he drops off in between, then there is no meaning. Or else suppose he traveled till this particular point in certain manner, then suddenly he started jumping to a different running race, and then actually he is traveling with a different velocity. Then this analysis is of no meaning. So what Rolle's theorem states is the function has to be continuous. The function has to be continuous in the closed interval. Closed interval a comma b. So closed interval we mean so all the values in between a and b, including a and b. So closed interval. All the values in between a and b, including a and b. So that is closed interval. So the function has to be continuous in the closed interval a and b. That is, this function should not be having any breakage in the entire travel of its journey. So till this point at least, right? So the function has to be continuous. And the function should be differentiable in the interval. So the function has to be differentiable in the open interval. A comma b. So interval a comma b, open interval we mean all the values in between a and b excluding a and b. That is open interval. Excluding a and b. That's what we call as open interval. Now, and f of a is equal to f of b, then there exists at least one point such that f dash, so f dash of c equal to 0, where c is in between a and b. So this is what is the Rolle's theorem states. Got it? So what Rolle's theorem states is, if the function is continuous in the closed interval a and b and differentiable in the open interval a and b, and f of a is equal to f of b, then there exists at least one point in between a and b such that f dash of c is equal to 0. So this is what is Rolle's theorem, that you can make out from the common sense, that if there is a function value, both are having the same magnitude, and we know that this function is continuous, and we know that the function is differentiable at every point, then there exists at least one point such that the slope has to be equal to the x-axis slope. Got it? Understood? So you can draw at least one tangent which is parallel to the x-axis. That's what it states. Now the question is, why we have to consider open interval for the differentiability? Why we have to consider open interval in the differentiability? Why can't it be closed interval? First you note down this, we are going to analyze that. Now you tell me why we have to keep open interval for differentiability and closed interval for continuity. Okay, so let me explain. See this, we are trying to identify in the region between a and b, and where we are interested in the closed interval a and b. That means all the points between a and b, including a and b. But here, if you wanted to find out the derivative at this particular point, or the way Vishal said, so the tangent slope, if you want to find out at this particular point, here you need to check the existence of the derivative at the point A. If you want to check the existence of the derivative at point A, then the prior information to point A you should be knowing. That means when we want to identify the derivative of any function, limit delta x tends to 0, f of x plus delta x minus f of x divided by delta x. So for this action, the limit should exist, then only we say that the function is differentiable at that particular point. Now here this delta x tends to 0. So this delta x can be 0 plus or 0 minus. Now for 0 plus you will be able to find out because on the right hand side you know, right? So very next to this A, if you can identify one point, you will be able to find out the value after A plus, then you will be knowing the right side limit. But what happens to the left side limit? Because you don't have any information about the function before A. So we are specifying our discussion to be in between A and B. That means if you don't know the prior information to the point A and after information to the point B, then you will not be able to find out the differentiability. That is why we will exclude the differentiability points of A and B. Got it? So that's exactly the reason we will check the open interval for differentiability. And there exists at least one point such that f dash of c is equal to 0 in the open interval a comma b, not in the closed interval, because we assured the derivative between the closed interval, so between the open interval a and b. Clear? That's why the value is in between a and b. So Raj, what I am saying is, if you wanted to identify the differentiation at this particular point, because we are trying to find out the derivative of the point when the slope is equal to 0, then that point may be A, that point may be B, or that point may be in between. Now the confusion is A and B also, if the points are included, the problem is you will not be able to find out the derivative at point A and point B, because the prior information to the point A or the prior information to the curve before A we don't know, and the information after point B you don't know. So without knowing that information, you will not be able to find out the left limit to point A and the right limit to point B. So, but if you wanted to assure the differentiability, this limit you need to check it. For this limit, the left limit for point A, you will not be able to check it, and the right limit to the point B, you will not be able to check it. Without knowing the left limit and right limit, you will not assure the differentiability at that particular point. That means differentiability, you cannot check it. You don't know whether it exists or not. Got it or not? Any other questions? Okay, great. So this is the Rolle's theorem. So here there exists at least one point. That means he has given the flexibility that there may be more than one point. Suppose this guy, even though we are checking the velocity at point A and point B, he might have taken different variations in his velocity during the entire travel. Now in this case, if you notice, this is one point where the slope is 0. This is one point where the slope is 0. This is one point where the slope is 0. Now at three different places he might be having the slope 0. That means there exists at least one point. That is the condition. There may be more. Clear? As long as all the three conditions, that is continuity between the closed interval A and B, differentiability in between A and B, open interval, and f of A is equal to f of B, then there exists at least one point such that f dash of c is equal to 0. Such that f dash of c equal to 0, Make this correction, equal to 0. Got it? Then the Lagrange's mean value theorem. So Lagrange's mean value theorem is also called as first mean value theorem, because Rolle's theorem forms one specific case of Lagrange's mean value theorem. So that is a little bit extension to this Rolle's theorem only, but that is more generic. Lagrange's mean value theorem, what it states is, earlier in case of Rolle's theorem, we have taken the function. So y is equal to f of x is the function, and this function you have considered one point a, and where the function value is a comma f of a, and another point you have considered at one more location, this point at b, and this point is b comma f of b. Now all the conditions of Rolle's theorem still holds good here. That is, the function has to be, so if the function is continuous in the closed interval a comma b and differentiable in the open interval a comma b, and f of a not equal to f of b, then there exists at least one point such that f dash of c is equal to f of b minus f of a divided by b minus a, where a less than c less than b. So this is what is called as, is stated by Lagrange's mean value theorem. So this is what is stated by Lagrange's mean value theorem. Now, by common sense, you can make out the Rolle's theorem is valid because actually we have identified practically how it is going to be true. Now, the same curve, there is a slope which is parallel to the x-axis. Now, I have shifted this axis to the some other axis. That means, if you draw a line like this, now there exists at least one point such that the slope at one random point should be definitely equal to the slope of this straight line. Correct or not? Understood or not? There exists at least one point such that the slope in between a and b is equal to the slope of this straight line. Clear? Right? So this is by common sense you can make out. The slope of this equation is f of b minus f of a divided by b minus a. So this is the slope of this straight line. There exists at least one point at point C where f dash of c, this is equal to f of b minus f of a divided by b minus a. This is what is stated by Lagrange's mean value theorem. Now the same analysis, if you tilt it to the horizontal axis, then this will become the x-axis, then the slope will become 0. Got it? So this is more generic statement. So that's why Lagrange's mean value theorem is also called as first mean value theorem. This is also called as first mean value theorem. Got it? So the same conditions of Rolle's theorem are satisfied here as well. But the only thing is f of a not equal to f of b. Then the slope should be equal to the derivative at one point. So minimum 1 point. There may be more. Note down this. Okay. Now, this one can also be written in a different format. So here f dash of c is equal to f of b minus f of a divided by b minus a. Here, if you simplify this equation in a different format, this is f of b is equal to b minus, so f of a plus b minus a times of f dash of c. Then here let b minus a, that is in between this length, so this I call as h. So if I call b minus a is equal to h, b minus a is equal to h, or b equal to a plus h. So if I replace it here, f of a plus h is equal to f of a plus h into f dash of c. This can also be written as f of a plus h into f dash of a plus h theta, where 0 less than theta less than 1. F of a plus h is equal to, this is what is called as Lagrange's mean value theorem. In remainder form. Got it? See this. What we have done is, we called b minus a, I have introduced a new letter h rather than b minus a. So b minus a is equal to h. Then b is equal to a plus h. Then I replace in the above Lagrange's mean value theorem. So this I have written in this format. I hope this is understood. Correct? From this to this is understood. I have written f of b on one side and rest of the things onto the other side. So f of a plus b minus a times of f dash of c. And here c is in between a and b. C value is in between a and b. That means it's more than a and less than b. C value, now actually I will replace at later point of time. So b can be written as a plus h, because this is starting point a and this distance is h. Then b can be written as a plus h. So f of a plus h is equal to f of a, and b minus a I treated as h, then f dash of c. And this f dash of c, this c value, we are sure that it is in between a and b, because it is stated by Lagrange's mean value theorem. If it is in between a and b, then what so the difference between a and b, I am calling this as h. Then this c value I can write as a plus h theta, where theta value is in between 0 and 1. Can I write this way? C value, h is this entire distance, and c value is in between these two. Then a plus h into some factor which is 0 to 1. That factor value, if I call 0.1, then a plus 0.1 into h will be definitely in between a and b. Suppose if I call this theta as 0.5, then it will be definitely a plus h by 2 will be in between these two. Now h is equal to, theta equal to 1, then it will be b. So that is a plus h. Suppose if I take theta value more than 1, then it is outside the range of a and b. That is invalid. That's why we state that f dash of a plus h theta, where 0 less than theta less than 1. Clear? Yeah. So any other questions? Yeah. So this is Lagrange's mean value theorem. And then Taylor's expansion is, this extension of this one is the Taylor's expansion. What Taylor's expansion states is, this f dash of a plus h theta is still further expanded with the help of Lagrange's mean value theorem again. Then this one, f of a plus h is equal to f of a plus h into f dash of a. So here actually f dash of a plus h theta you can treat as g of x. Then here actually if you apply the Lagrange's mean value theorem between these 2 points, then this will be further expanded, where the function is the derivative function of the original function f. So that's why h into f dash of a plus h square by 2 factorial into f double dash of a plus h theta. So this is one step extension. Got it? Similarly, if you extend for one more, then it will be f of a plus h into f dash of a plus h square by 2 factorial into f double dash of a plus h cube by 3 factorial into f triple dash of a plus h theta. So this way you can extend to any number of terms you want. So if you extend for infinite number of terms, we call that as Taylor's expansion. So this is also called as Taylor's expansion. Got it? Understood? Okay, so note down this Taylor's expansion. Fine. So from this, what we can make out is the Taylor's expansion for any number of terms. You can write it. So f of a plus h is equal to f of a plus h into f dash of a plus h square by 2 factorial into f double dash of a plus h cube by 3 factorial f triple dash of a plus dash 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 h power n by n factorial into f of a plus h theta. Got it? So this is the Taylor's expansion. Taylor's expansion with remainder. Now the extension of this Taylor's expansion. So the extension of the Taylor's expansion. So nth derivative exactly. Yeah. The extension of this Taylor's expansion is nothing but Maclaurin's expansion. So this is the extension of Taylor's expansion. So this Taylor's expansion is extended between any point from point A, right? Now, if I randomly give a function, suppose I call y is equal to or f of x is equal to e power x, then this e power x I wanted to expand with the help of Taylor's expansion. Now, with the help of Taylor's expansion, if you wanted to expand, that has to be from any point starting from point A. It will be counted, right? Now, the Maclaurin's expansion and Taylor's expansion, the basic difference is the function is expanded about origin. Suppose if this is the function, then take this particular point and then try to expand around this particular function. Got it or not? That means what it essentially means for us is here out of a plus h, treat a is equal to 0 and h is equal to x. Then this will become Taylor's expansion and this will become Maclaurin's expansion. So rather than taking the point here, you always starts with 0. That is suggested by Maclaurin. So start with 0 and then if you take any point, definitely starting from 0, this value will be x, b will be always x, right? Correct or not? So h is equal to a plus b. So h is equal to x. So if h is equal to x, then b is equal to a plus h. So a is 0 and b is x. So b is again x. So this is the condition of Maclaurin series. That means you are starting with 0. Rather than expanding it, you will be doing the Taylor's expansion here. This is what we call as the Maclaurin's expansion. Clear? Then the Maclaurin's expansion will be f of a plus h. H will be x. So a is 0. Then f of x is equal to then f of 0 plus x into f dash of 0 plus x square by 2 factorial into f double dash of 0 plus dash 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 up to infinite. This is the Maclaurin's expansion and most famous expansion, and this is very, very important. So why? Because this is one of the greatest tool which will convert any random function or any non-linear function, right, to a polynomial. So this is a polynomial which involves only the powers of x. No other things are involved. You give me any function, whether it is a logarithmic function, trigonometric function, or any random exponential function, you give that function, it will convert into a polynomial. So this is the greatest thing about the Maclaurin series. Now here, e power x expansion, if you want to do it, see this, f of x is equal to e power x. Then f of 0 is equal to e power 0 is equal to 1. Then f dash of x is again equal to e power x. Then f dash of 0 is also 1. And f double dash of 0 is also 1. So whatever may be the derivative in this particular case, so the value is always coming out to be 0. Then this expansion e power x can be written as f of 0 is 1 plus x into f dash of 0 is again 1 plus x square by 2 factorial into 1 plus x cube by 3 factorial into 1 plus dash 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 up to infinite. This is the Maclaurin series. So if you want, so we know the value of E is 2.1, so 2.71828. How we got it? With the help of computers, we will be using only this expansion and finding out that value. So in the calculator, whatever is shown, right, that is found with this expansion only. Because calculator don't know how to directly calculate this value unless we have the Maclaurin's expansion. This is the only principle that is getting used there. So here, if x is equal to 1, then 1 plus 1 plus 1 by 2 plus 1 by 6. So this itself actually, you can be sure that 1 plus 1 is 2, 2 plus 0.5 is 2.5, then 0.1 is so 2.6. So definitely we can be sure that the value is definitely greater than 2.6 and almost lesser than 2.8 because this value keeps on reduces in a exponential way. So the value will be somewhere around 2.7. So this itself you can make out. That means the Maclaurin series is one of the greatest tool for finding out the approximate values of the function. So if you are able to compromise the calculations from this onwards, you can be sure that the E value will be 2.6. Straight away you can find it out. So you are compromising the accuracy from 2.7 to 2.6. That is 0.1 is the compromise. But the calculation will be pretty straightforward, and by looking at the function itself, you will be able to get it. So that is the advantage of this Maclaurin series, which we are going to use for the error approximations at multiple locations in the physics. Clear? Got it? Okay. So you can note down this. So these are the fundamental theorems that we have to be aware in case of this mean value theorems. And one more theorem, that is Lagrange's mean value, Cauchy's mean value theorem. That is also more or less falls under the similar lines. Cauchy's mean value theorem, it talks about two different functions. So what Cauchy's mean value theorem states is, if there are two different functions, let us say this is one function and this is one function, then I have taken two different locations like this. So I call this as f of x and I call this as g of x. Then this is point A and this is point B. Then you can draw a straight line between these 2 points. This is a comma f of A is this point, and b comma f of b is this point. Then this point will be a comma g of a is this point and b comma g of b is this point. Then if you draw a straight line between these two, then as per the Lagrange's mean value theorem, there exists at least one point such that f dash of c is equal to f of b minus f of a divided by b minus a. So this is Lagrange's mean value theorem. Similarly, g dash c is equal to g of b minus g of a divided by b minus a. So this is also Lagrange's mean value theorem for the function g. Now the conditions are the functions both f of x and g of x should be continuous in the closed interval a comma b and differentiable in the open interval a comma b, and f of a is not equal to f of b and g of b is not equal to g of a. Then there exists at least one point such that the ratio between these two, f dash of c divided by g dash of c, is equal to f of b minus f of a divided by g of b minus g of a. So this is the Cauchy's mean value theorem, wherein g dash of c not equal to 0. Then only this condition is applicable. Got it? This is Cauchy's mean value theorem. So you can state all the rules, whatever I just spoke, right? Then the ratio between the slopes, that means there exists at least one point in between these two such that this point is C, wherein if you draw a tangent here, this slope, and draw a tangent at this point, then the ratio of these slopes is equal to the ratio of the straight line slopes. Got it? So ratio of tangent slopes is equal to ratio of the straight line slopes. So this is the condition. Got it? This is Cauchy's mean value theorem states. Any questions? Okay, so is it clear? Concept wise, I hope everybody is clear, right? Okay, so in that case, right, so in the next class, I'm going to solve the problems based on all these aspects, that is Lagrange's mean value theorem, Rolle's theorem, and Cauchy's mean value theorem, and Taylor's expansion and Maclaurin's expansion also, because that takes more time. Clear? Okay, so and then I have given one assignment also. I hope everybody will be able to solve that. I have given the solutions also, so you try to check the solutions. Clear? Okay, so thank you. A good night.